The video study guide for the Chapter 7 test on exponential functions and logarithms. Now, we're going to quickly, all the questions from 7.1 to 7.4, I'm going to go through those really fast. If you want a more detailed explanation of those, you can see the previous video study guide that I did for the quiz there. So, numbers 1 through 4, you should automatically know that numbers 1, that's going to be a decay because the base of the thing that you're raising to an exponent, we call it the base, is less than 1. And that's the only one that's decay. Whereas all the others are growth because the base is a number that is bigger than 1. So decay for number 1 and growth for all the other three. If you can't remember why E, like that's growth, you can run it in your calculator, but E is approximately 2.718. And again, that button in your calculator, there's two places to get to it. You can do second and you can hit the division key. But even if I want to find out what E is, I use the second natural log button and I just raise E to the first power. So that's why that one's growth. Now, as far as the Y-intercept is simply the number that is in front of the exponent. So the Y-intercept for this one is going to be, number 1 is going to be 3 or 0, 3. For number 2, the Y-intercept is going to be the number 2 because it's, the thing in front here. And for number 3, the Y-intercept is going to be, again, the coefficient in front of there is 0.1 or 1/10. And the Y-intercept for number 4 is going to be the 3. You can confirm all of those by graphing them, but decay, if it's less, the base is less than 1, and the Y-intercept is always, the coefficient that's in front of the base that you're raising to an exponent. All right, going next on to how we transform exponential functions. You should know that this plus 2 right here, that's a vertical shift up by 2. You should know that this plus 1, since it's really close to the x, that's going left by 1. And similarly, this one right here, that's a shift left by 2. And the other things of note, like, so this is the parent function, the number 5, it's only shifted up by 2, which does not affect its range. It doesn't affect its domain, but its range, instead of going from 0 to infinity, is going to be moved up by 2, so its range will now be 2 to infinity. And that's for number 5. For number 6, again, the domain isn't affected, even though it's moved to the left by 1. If you subtract 1 from both of these infinities, you still get infinity. So you can't really affect the domain when your original domain is all real numbers. But the range is going to be the standard range from 0 to infinity. And you can look at the graph to kind of confirm that. For the last one, as far as the domain and range, we don't just, like this, you can't really affect the domain. So we don't care about the 2, even though it's shifted left by 2. The negative is definitely going to have an impact on the domain. Still all real numbers. You could write that in any notation you want. But the range, what does the negative do? Negatives flip it upside down. So instead of a normal exponential function going like this, it's going to flip it upside down. So for number 7, the range will be, instead of 0 to positive infinity, it'll be 0 to negative infinity. But we like to write the low numbers first. So negative infinity to 0 is a better way of saying that. As far as the asymptotes are just where the graph kind of like follows a line. For the last 2, the asymptotes are going to be y equals 0 because that's the line that the graph comes really close to but never crosses. But let's look at number 5. So I put this into my equation. I'm just going to go to the standard window. And what an asymptote is, if you remember, it's what the line like kind of comes. So for this one, and it's really given by if you have your range, whatever number your range kind of stops at, that's a good indicator of where you're going to likely have an asymptote. So for the 6 and 7, the asymptote is just the x-axis itself. You could say the x-axis, or you could say the line to y equals 0. For number 5, the asymptote is just simply the line y equals 2. So you need to know how these numbers shift, reflect, Also, the number 6, like the 1/2, makes this thing shorter. The vertical compression here, and you need to be able to answer questions about domain and range and asymptotes. In general, the asymptote is going to be at the x-axis for exponential functions, but if it's shifted up or down, then the asymptote will be shifted up or down likewise. Reviewing logarithms, you should know that when you go from writing something into exponential form or logarithms, we always put the base right after the word log, then we put the result, and you put the power on the other side. So this as a logarithm is log base 5 of 625 is equal to 4. For this one right here, there's really two ways to write it, but you start with the base, you put the result, and then you write the power last on the other side. So this is log base e of 1 is equal to 0, but log base e, uh, there's a special expression we have for that is natural log. So natural log of 1 equals 0. And if you want, you can put parentheses, like your calculator does parentheses. When we write them by hand, we typically do not put the parentheses, but it's not wrong to put them. If anything, worst case scenario, it just makes it more clear. So either of these ways to write it. For this one, it's awkward to put log base e. You should write natural log whenever you're writing something log base e. When we're evaluating logarithms, of course you could use your calculator to do this, but the most important thing is, do you understand what question is being asked? This is asking what power do you raise 2 to get 8? We raised 2 to the power of 3 to get 8, so the answer is 3 for this. For number 11, what power do you raise 7 to get 7? So 7 to what power gives you 7? Well, of course, 7 to the first power is 7. What power do you raise 5 to get 1 over 125? Well, I know that 5 to the third is 125. And I know that, oh wait, that's how these are related. Oh, but I know that if I have a negative power, it gives me a reciprocal. So the answer to this one is -3. And for this one, what power do we raise 11 to get 1? Well, the answer would be the same regardless of what the base was. If you raise anything to the 0 power, you get 1. Again, all of these can be done in your calculator by either doing, like for instance, let's do this one right here in my calculator. You can use the log base button, log base 11 of 1 like that, or if you don't have that feature in your calculator, you can enter it this way, log of 11 divided by log of 1, log of 11 divided by, actually I'm backwards, sorry. I'm supposed to put log of 1 divided by log of 11. Whenever you're using the change of base formula, you always put the big number on top and you put the base on the bottom. So it's like that. You can run all these in your calculator either way you want, but some don't require a calculator, especially when the answer is not a decimal. This is similar to numbers 4, 5, 6, and 7, but instead of being asked about exponential functions, we're talking about logs. So some things you should understand. This -1 next to the x, you should know that that's a shift to the right. Similarly, this +2 next to the x is a shift left. Okay, and then this 1/2 you should know is a vertical compression, so that's going to make it shorter. Similarly, so we don't have anything next to the x, so it's not shifted right or left. But then we have a 1 minus this. Let me actually change the order of this. Instead of saying 1 minus log, I could say negative log base 2 of x, and then add 1. This is a vertical shift up. So that's moving up, and then the negative, of course, reflects it and makes it go upside down. So when we're talking about domain and range, it's good to know the basic domain and range of a log function. It's the inverse of how it works for exponential functions. So just like the range of a exponential function is -infinity to infinity, the domain of a log function is the same. Just like the domain of an exponential function is 0 to infinity, well, similarly, the range is typically of a log function is 0 to infinity. I'm sorry, I got that backwards. So this is for exponential functions, okay? The domain is -infinity to infinity, the range is this. But for logarithmic functions, it's swapped, okay? Because they're inverse functions. So of most logs, the domain will be 0 to infinity, and the range will be all real numbers because they are inverse functions. Now, let's look at how 14 is changed from the general form. So I'm looking at my general rules. It's usually 0 to infinity, but it's shifted right by 1. That means my domain for number 14, instead of being 0 to infinity, shifted right, 1 to infinity. And then the range, you're not gonna mess with negative infinity to infinity, so it's kind of not really important to write. For number 15, well, this one shifted to the left by 2. So for number 15, the domain, instead of being 0 to infinity like most logs, it's going to be shifted to the left by 2. So it's going to be negative 2 to infinity for the domain, whereas the range is all reals. And finally, for number 16, your domain isn't affected at all because it's not shifted left or right. And even though it's shifted up by 1, when you add 1 to infinity, you can't modify the range when it's negative infinity to infinity. So your domain and your range for this one is going to be the same as whatever the standard logarithmic function is. The asymptotes, again, just like the asymptote for an exponential function, your asymptotes for an exponential function are typically at y equals 0, but if you shift them up or down, that's going to change. So it's usually y equals 0, but whatever vertical shift you give to them in an exponential function will change the vertical asymptote. Similarly, in logarithmic functions, your asymptotes are going to be the line x equals 0 because the domain and the range are swapped. So for this first one, your asymptotes here for a number, I'm just abbreviating ASY for asymptote. Your asymptote is going to be x equals 1. For number 15, your asymptote is going to be at x equals negative 2. And then for number 16, your asymptote is going to be, we didn't mess with the domain at all, so it's going to stay at x equals 0. Again, you can graph those if you want, but the calculator does a really bad job of graphing the vertical asymptotes. And I'll show you by putting this into the calculator. Because the calculator is so afraid to graph vertical lines, I know this should have an asymptote for number, let me actually, I mixed two of the functions there. Let me do number 15. If I try to graph this, I know I expect the vertical asymptote at x equals 2, but your calculator is afraid to graph what is essentially practically a vertical line. So you might not believe that the range of logs is negative infinity to infinity, but if you use other applications to graph, TI-84s are really bad at graphing the negative range of logs. And so I can show you on another graphing application. Notice how the range does go to negative infinity, but not all pieces of technology like to graph what it thinks is a vertical line. So that's why the importance of understanding that logarithms are inverse functions of exponential functions, which we learned in the Gizmo, we talked about it countless times, is core to our understanding of logs. But the graphs can be helpful. You can get a lot of mileage out of graphing it. You just can't get it always perfectly there. Now, as far as the Y-intercepts, Y-intercepts are really easy to find. You just plug 0 into the equation. So for 14, I just plug 0 into that equation, and notice how it gives me an imaginary number. So a y-intercept, again, is when the x is equal to 0. So that means, since it's imaginary, that means there is no y-intercept for number 14, which makes sense because there is no 0 in the domain. So that checks out with our logic. For number 15, if you want to find the y-intercept, you can try to do it by hand, but I'm going to use the calculator. By replacing the x coordinate with a 0, my y-intercept is going to be 0, comma, 0.315. I can round to whatever I need. All of these do have an x-intercept, but like the first one doesn't have a y-intercept, but the second one will, again, because 0 is in the domain, so we expect that. Now, what about this one? Is 0 in the domain of number 16? Well, not quite. There's a parenthesis here. So if you evaluate this function, number 16, if you try to evaluate it at 0, and the only reason mine's even spitting imaginary numbers is because I have it in that imaginary mode. Otherwise, it will kick out an error, but most logarithmic functions, unless you shift them over to the left, won't have y-intercepts. This is from section 7.4, so we're getting on the last of the material that's reviewing that we already did on the quiz. If you want to write this as a single log, separated addition is combined multiplication, but before I combine that, I move this 3, become a power right here. So that's log of 4 times 9 to the third power. And that's the answer that I'm looking for. Of course, I could simplify. I could, compute whatever 4 times 9 to the third, which is this number right here, 2,916. But we want to write it as a log. Don't actually evaluate the log base 2. I forgot the 2 there of that number. You should write out log base 2 of the 2,916. And really, again, these questions are going to be multiple choice ones, so you're not going to make a mistake of evaluating it if they ask for something in terms of the log. This one's log base 10, but again, before we start applying the quotient rule, because the separated subtraction means we do quotient rule, move this 3 on top of the A, move this 2 on top of the B, so we have a single log written, but A cubed over B squared. So that's the quotient rule and the quotient property and power property in the same question. For numbers 19 and 20, we're doing those in reverse. So combined division is separated subtraction. So log of A minus the log, whatever the base is, of B. So we're just doing like what we did in number 18, but backwards. So this one, these are all combined to multiplication. So that means separately you add them. So you got log of 3 plus log of x cubed plus log of y squared. And since we're expanding it, so that even though that's all separated, now I can take this 3, I can apply the power property backwards. That's 3 log of x plus 2 log of y. And once again, these will always be, whenever you encounter these, it usually be in multiple choice form. For number 21 and 22, we're just going to practice a little more with evaluating these using those properties. They can be done by hand, but I know that since we can use a calculator when we need to use it to represent these, I'm not really going to work these in detail. But for instance, we know that log 9 base 9, that's just a 1. Log 9 base 27 might be a little harder to do, but you could reinterpret log as log 9 and log 27. Reinterpret the 9 as 3 to the second power. And then 27 is a 3 to the third power. So this is going to end up being like a 2/3 relationship. But you're not going to have any like this on the test. They're because when we actually practically use logs, we want to focus mostly on like practical applications. If you notice, yeah, it's 1.5. So all I can say is this 2 and this 3 makes this come out to like a 3/2 power is what it is. But don't be too concerned with numbers 21 and 22. Even though they can be done by hand, only on a test, say, where you weren't allowed to use a calculator. If you're in a course where they don't let you use a calculator, would you really be concerned with these? But you're allowed to use a calculator, so unless you're taking like the second part of the SAT math, then you don't necessarily need to like practice these. If you want to practice these on your own, you can. But number 21 and 22 will not be items that you'll be tested on in my class. So here we're going to solve equations. So this is stuff that we haven't done on the quiz. So we're going to start to take it a lot slower here. We're going to write the equations, and you need to remember, I want to solve for an exponent. How do I get this exponent down? You would be wrong if you say subtract 27. You'd be wrong if you said divide by 27. You can't do any square root or cube root. All of that is not going to work out. The way you have to do it is, well, we have exponents. A variable is in the exponent. How do you get it down? You use logs. You can use log or ln. It doesn't matter what base log you use. I'm going to use ln for all of these pretty much just because I can. But you can use log if you want, just like we've done in class. So if you use that, use the power property, the 3x gets brought down. So you get 3x times natural log of 27 equals natural log of 18. And then you just divide by the 3 to get that 3 away from the x, and also divide by the natural log of 27 to get rid of that. Divide that on both sides, enter that in your calculator, and that's your answer, which comes out to about 0.29. Just to show you that it would, I put the answer using log instead of ln, and look, they come out to the exact same answer. So any base log you use, whether it's base e, base 10, base potato, it's going to come out to the same answer. So you get x is equal to, let's do 3 decimal places, 0.292. I'm going to be asking to round to the nearest thousandth on the test. For number 24, we kind of start the same way. The most important thing you need to know that if you have a variable in an exponent, you have to know that you need to be using logs to solve that. If you don't at least know that, you are in a heap of trouble. So first thing you do is log, either log or ln, whatever, both sides. It brings the exponent down using the power property, so you get x minus 1, natural log of 3. You should put this in parentheses, equals natural log or log of 24 if you use the log button. And then you just want to get x by itself. Well, there's multiplication happening right here, so divide by natural log of 3. And then after you divide by that natural log of 3 on both sides, we can to be x minus 1 by itself. How do you solve for x? You add 1 on each side, and then you just run this in your calculator. So you can use the alpha y equals button, but I used that last time just in case you have a calculator that can't do that. Let's say you don't have the alpha y equals button. When you enter this in, make sure you close the parentheses on the natural log of 24 before you start doing the natural log of 3 on the bottom. And then we can take that and add 1 to it, and this is your answer. And again, we'll round to 3 decimal places, so 3.89. So your value of x is equal to 3.893. And remember, you can always guess and check this. You can use solve by graphing to solve this too, but solving by graphing, the reason we want to focus on the algebraic way, not only is it more efficient, and it's a better way of doing it, but finding the right window for doing it by graphing it gets kind of. For 25, there's actually a clear advantage in using log here, but the most important thing is that you know that to solve equations with exponents in it, you have to log both sides. I'm going to use ln. I just prefer to use that one. And again, we use the power property. That 3x gets to be kind of brought down in front, so we rewrite this. 3x times natural log of, actually, I'm not allowed to do this yet. Let me back up here. Before I can natural log both sides, let me get rid of this coefficient too, because it's like before there was just like the base and its exponent. For number 23, we had just the base and its exponent on the left side. But here we have the base, the exponent, but there's this coefficient. So that makes it to where we can't log quite yet. Let's get rid of this 2 by dividing it out. So we get e to the 3x power is equal to 8, or you could leave it as 16 over 2 if you want. And then we want to start using the log property to get that 3x down. Rewrite this. You get 3x times natural log of e is equal to natural log of 8. Now, I happen to know that natural log of e is 1, and you can know that too. You really should know that. But if you do natural log of e to the first power, the same thing as just saying e, it gives you 1. Let's say you didn't know that. It's just like you didn't know that at all. All right, I'm still going to divide it out. I want to get x by itself, right? It's being multiplied by the natural log of e. It's being multiplied by 3. So I'm going to divide by 3, and I'm going to divide by natural log of e. So like those cancel out. If I did it to the left, I have to do it to the right. So divide by 3 natural log of e, which is the same thing as just dividing by 3 since this is equal to 1. So x is equal to whatever my calculator tells me this is. So I get natural log of 8 divided by 3, or if you want natural log of 8 divided by 3 times natural log of e, And notice how they give me the same answer either way. And round to, 2 or 3 decimal places. So if I round to 3 decimal places, I get 0.693 as the value of x. For number 26, it's a little different from the previous three because instead of solving an exponential equation, I'm solving a logarithmic equation. There's many ways to look at this. I'm going to solve it three ways really fast. So I can divide the 2 out. So I get log of x is equal to, if you simplify this, this comes out to -2. And it's like, well, where do I go from here? Well, there's a few ways to do this. This is really log base 10. The 10 is understood. So if you take 10 and raise it to this power, the 10 and the log base 10 cancel out. So if I did that to the left side, do it to the right side, make it 10 to the -2nd power. So you get x equals 10 to the -2nd. If you run that in your calculator, you get 0.01. Here's another way of looking at it. Let's say you want to use the power. So you start with 2 log base 10 of x is equal to -4. If you want to use the power property and like put that 2 right here, that's log of x squared is equal to -4. And then you can still do the same thing. You can do the 10 on both sides here, and these cancel. And so you get x squared is equal to 10 to the -4th. And if you square root both sides, you get x again is equal to 0.01. And I don't have to worry about in this case, I don't have to worry about the plus or minus case because if you, like, say you did the plus or minus thing, if you make x equal to -0.01, since that's not in the domain here, you can't put a negative here, that's not a valid solution. Last way we're going to do it, again, the first one's my favorite, but you could also reinterpret once you get to here. Just rewrite this logarithm as, okay, here's the question. 10 to the -2nd power is equal to x, which is exactly what we have here. So that's really a repeat of the first one. But that's how you solve a logarithmic equation, is you use exponents to undo the logs. For numbers 27 through 30, really all I care that you know is that for the change of base formula, these are equivalent. If you remember, we had a question like this on the quiz. Log base 3 of 16 is the same thing as log of 16 divided by log of 3. And it's similar for all the others, where you put the big number is log that big number divided by log that little number, which we call the base. And that's true for all of these. So, and you're asked to like use this to rewrite each of these. But the idea is that knowing these are equivalent gives you two ways to run it into your calculator, either using the log base button or just doing log of the big minus log of the small. Okay, for these last few, we're just going to get a little more practice with solving logarithmic equations. We're going to start with number 30. And I will say that these problems most of these are going to be on the honors only part of the exam, specifically number 32 and 33. Those are going to be two of them that have like a slightly higher degree of difficulty. 33 will actually have two solutions. But for everyone else, 31 and 34, you should have an idea of at least how to rewrite these to start solving them. So for 30, before we can, undo this natural log by, either rewriting it or raising, doing e to the left side and e to the right side, you have to use this property. So this is good practice for that property. This is natural log of 2 times x equals 1. So I just rewrote this left side. So everyone should know how to at least rewrite that. And then if you want to get rid of the natural log, you use the e function to cancel that out, get the inverse function. So you get 2x is equal to e to the first power, and then you just divide by 2 on both sides. So you get x is equal to e to the first power divided by 2. So the most important part is that you understand how to rewrite this before you can even start this. For number 32, we're going to apply that same property we did last time. Log of a plus log of b is equal to log of a times b. So we're going to take this x plus 1 and this x minus 1 and put it all inside of one log, set that equal to 4. If you FOIL this or distributive property, whatever you want to call it, This is the natural log of x squared minus 1. All I did was just do x squared minus x plus x. Those cancel out. Negative 1 times 1 times positive 1 is the 1. And that's equal to 4. And then we do the same thing we did before to get rid of natural log, because the natural log, the base of natural log is e. So do e to that power, and then these cancel out. It drops down to x squared minus 1. Here we have e to the 4th on the right side. And then move the 1 over, then square root both sides. So we move the 1 over, square root both sides, and then run that on your calculator, and you get 7.456 around. But knowing how to apply those properties, that this is the product property, again, just like 31, is the most important first step. Otherwise, you can't go anywhere. For number 33, since it's already one natural log, so the good news is we can go right into, we already have a natural log, a single natural log by itself, so we can already kind of cancel that out with an e. So this drops to 2x minus 1, the second power equals e to the 7. All right, and I want to get at the x, but it's trapped. First, it's trapped inside of something squared. Then I got to add that 1. Then I got to divide by 2. So to get rid of the little exponent of 2, I'm going to square root both sides. And remember, when you square root, you might have to deal with a positive and negative case. So I'm going to do plus or minus square root of e to the 7th. And then I want to move the 1 over on each side, rewrite it, and then I want to divide by the 2 on each side. And instead of putting the 1 on the end, I chose to put it in front. So 1 plus positive e to the 7, square root of e to the 7th over 2, 1 minus square root of e to the 7th over 2. Then you run that in your calculator. For one of the solutions, you get 17.058 if you do 3 decimal places. And then for the negative case, I'm just going to grab that, change that to a minus. You get negative 16.05. So those are actually both. This is going to be a problem with 2 solutions. And again, you'll basically always have 2 solutions anytime you have the thing that's being natural log if it's being squared. And these are your 2 solutions. This time we don't throw the negative solution away because it's, the negative solution doesn't make us have a bad value inside of the natural log there, because we end up squaring the thing anyway. So even if it makes the 2x minus 1 negative, that gets squared before we natural log it. And you can only natural log or log anything log positive numbers. For number 34, again, we want to, before we e both sides, we want to get it to where everything, like there's only one natural log. We have to use those properties. The power property here is natural log of x cubed minus natural log of 2. So, but now I want a single natural log. We're subtracting, that's separated. So that means if you combine them, it's all one thing, but as a quotient. That's the quotient property right there. Now we can, do the inverse function of natural log, which is e to that thing. These cancel out. You get x cubed over 2 equals e over 4th. We're going to multiply by 2 on both sides, cancel out the 2. So you got 2 times e to the 4th. And then we cube root that result. So we get x is equal to cube root of 2 times e to the 4th power. And remember, to do cube root, you can either do a 1/3 power, or if you go into your calculator, if math 4, you'll see. So if you do it that way, you get about 4.7779 or 4.780. But you could also raise it to the 1/3 power. If you raise it to the 1/3 power instead of cube rooting, you get the exact same result. So you get 4.78 whether you round to the nearest hundredth or 1,000th in this case. Just if you put the 0, that just shows the root that you rounded to the nearest 1,000th, kind of like you're doing. For number 35 here, this is just practice and showing that it doesn't matter what base log you use. So if you take the original equation, 3 to the 2x is equal to 4. If you use log base 3 to solve the equation? So if I log base 3 both sides of the equation, yes, it's nice. It like cancels this out. And you get 3x is equal to log base 3 of 4. And then to solve for x, you divide by 3. And made a little mistake here. Sorry, I misread that. That's not a 3x. That's a 2x. So that's a 2. That's a 2 right there, which makes this a 2. And then we put a 2 right there. And so you get 0.630 or 0.631 if you round, do it that way. If you use common logs, which is log base 10, they don't cancel out like this because the base of this is 10, the base of this is 3. They don't cancel out that way, but you can still use the power rule. And so you get 2x times log of 3 equals log of 4. And then we do something kind of similar. We do x is equal to, this time we do log of 4 divide by the 2 and the log of 3, which equivalently, like it's going to be the exact same thing. Since log 4 over log 3 is log base 3 of 4, this will also, if you enter it in your calculator, come out to that same value. Comes out to the same value of 0.631 if you round. Bar 36, the most important thing you understand. So exponential growth, you can kind of use, let's use money as a model. So if I invest $1,000 and I want it to grow at 13%, I prefer to use T for the variable because it does that over time. So the amount of money that I have increases by 13%. This would be exponential growth. Whereas if I want to do exponential decay, let's say I invest $1,000, but instead of appreciating, it depreciates. Maybe a better example is, say you buy a car for $1,000 because cars depreciate. This would be a depreciation by 20% every year. So growth, if the base is bigger than 1, you have decay whenever your base is less than 1. And last one, I can guarantee you will have one like this on the test. So on the quiz, you were given, continuously compounded interest, but I gave you the amount of years, and I wanted you to tell me how long, after how many years, what money would you get. Here, instead of being given, we're still using the PERT formula, but instead of being given the time, we're going to solve for the time. So we know that you put 1,500 in, so that's the principal, that's the initial investment. And then E is a number. The rate is 7%, but don't put the number 7. 7% as a decimal is 0.07. And then we multiply that by the time, but we don't know the time. What we do know is we want to know how long it takes for that to grow to be $2,000. And we're going to use logs eventually to solve for this. But again, before we can log, we got to get like the base by itself, just base and exponent. We have a coefficient. We don't want that coefficient there. So let's divide it out. And so that cancels out on this side. And then we have just the E and the base here. So I'm going to rewrite this. And now that's rewritten. I'm going to natural log both sides. You could use common log, but I mean, natural log just does the neat thing of this cancel out and it's dropping. And we natural logged here. I don't need to write parentheses, but I really prefer to write parentheses. It just looks safer to me. And so I'm going to scroll down a little bit. And we have if I rewrite this, that this natural log of this quotient is equal to 0.07 times t. All I have left to do, since that we did the natural log of that side and the exponent kind of drops down, we're kind of using the power property here. You can see it as it got brought in front. And this became natural log of e, which is 1. Right here, all we have left to do is divide by 0.07. And once you enter that in your calculator, that tells you how many years it takes $1,500 at a 7% interest rate compounded continuously to grow to 2. So I just type that in my calculator, natural log of that quotient, and then take that and divide by 0.07, and you get about 4 years. So, and if you round, let's round to 2 decimal places here. So that 0 gets rounded up to 1. So that's about 4.11 years. And that's it. That's it. Again, for the earlier questions, if you want to see those done a little slower, you can look at the quiz. But the new stuff is really focusing on solving these, when you're solving for the exponent. That's the thing that's new on the test that was not on the quiz.